Welcome to our lesson on the binomial distribution. Today, we'll learn about one of the most important probability distributions in statistics. First, let's understand when to use the binomial distribution. The binomial distribution is applicable when we have repeated independent trials with exactly two outcomes for each trial. We need to have a fixed number of trials, which we denote as n. Each trial must have exactly two possible outcomes: success with probability p, or failure with probability q, where q equals 1 minus p. Let's define the binomial distribution. Let capital X represent the number of successes in n trials. Then we say X follows a binomial distribution with parameters n and p, which we write as X is distributed as bin n p. The probability mass function, or PMF, gives the probability of getting exactly k successes in n trials. The formula is P of X equals K equals n choose K times P to the power K times 1 minus P to the power n minus K, where K can range from 0 to n. Here, n choose K represents the binomial coefficient, which is calculated as n factorial divided by k factorial times n minus k factorial. Let's visualize what the probability mass function looks like for a specific example. Consider a fair coin with P equals 0.5, tossed 6 times. The graph shows the probability of getting exactly k heads for each possible value of k from 0 to 6. Notice that since the probability is 0.5, the distribution is symmetric around k equals 3. Now, let's talk about the mean and variance of the binomial distribution. The mean or expected value of x is simply n times p. The variance of x is given by n times p times 1 minus p. For our example of tossing a fair coin 6 times, the mean is 6 times 0.5, which equals 3. The variance is 6 times 0.5 times 0.5, which equals 1.5. Often, we're interested in cumulative probabilities rather than exact probabilities. For instance, we might want to know the probability of getting at most k successes, which is the sum of probabilities from 0 to k, or we might want to know the probability of at least k successes, which can be calculated as 1 minus the probability of at most k minus 1 successes. Let's visualize the cumulative distribution function for our coin toss example. The graph shows the probability of getting at most k heads when tossing a fair coin 6 times. Notice how the curve starts at the probability of getting 0 heads and increases until it reaches 1 at k equals 6, since the probability of getting at most 6 heads in 6 tosses is 100%. Let's work through a complete example. A fair coin with p equals 0.5 is tossed 5 times. What's the probability of getting exactly 3 heads? Using our formula, P of X equals 3 is 5 choose 3 times 0.5 to the power of 3 times 0.5 to the power of 2. First, let's calculate 5 choose 3, which is 5 factorial divided by 3 factorial times 2 factorial. That's 10. Next, 0.5 to the power of 3 times 0.5 to the power of 2 is 0.5 to the power of 5, which is 1 over 32. Finally, 10 times 1 over 32 equals 10 over 32, which is 0.3125. Let's now look at the common types of problems you'll encounter. First, you might be asked to calculate the probability of an exact number of successes. You might also need to find the probability of getting at least, at most, or between a certain number of successes, which involves using cumulative sums. Finally, you might be asked to find n or p given information about the mean or variance. Let's solve a practice example to solidify our understanding. A biased die has a probability of showing a 6 equal to 0.2. It is rolled 10 times. What is the probability of getting exactly 2 SIXS? Using the formula, that's 10 choose 2 times 0.2 squared times 0.8 to the power of 8. What is the probability of getting at least 1 6? This is 1 minus the probability of getting number SIXS, which is 1 minus 0.8 to the power of 10. Here are some tips to help you with binomial distribution problems. Always check that the trials are independent and that the probability of success is constant. For large values of n, consider using a calculator or binomial tables to calculate probabilities. Remember the connection to the binomial expansion theorem from algebra, which is q plus p to the power of n. To summarize, the binomial distribution is used when we have a fixed number of independent trials, each with the same probability of success. we discussed the probability mass function, mean, variance, and cumulative probabilities. We also worked through examples to apply these concepts. The binomial distribution is a fundamental concept in probability theory and statistics with many real-world applications. Thank you for watching this video on the binomial distribution.